Hey everyone, I'm Alex, and I'll be presenting joint work with Justin Holmgren and Ron Rothblum on Fiat-Shamir via list-recoverable codes. First, here's a short summary of what we do in this work. We give a new instantiation of the Fiat-Shamir heuristic in the standard model for a fairly broad class of interactive protocols. For example, we can compile parallel repetitions of any commit and open protocol with the right commitment scheme used. And how do we do this? We leverage a new connection between Fiat-Shamir and list-recoverable codes. So before getting into any more details on that, let me give a motivating example from introductory cryptography. So if you were to explain to an undergrad how to construct zero-knowledge proofs for all of NP, you're likely to go through the seminal work of Goldreich, McCauley, and Vigderson, who give a protocol for the NP-complete problem of three coloring. This protocol, the prover proves knowledge of a three coloring of a graph to a verifier by sending a commitment of a randomized version of that coloring and waiting for the verifier to ask to open up a single edge in this coloring. The verifier then accepts as long as the prover reveals two distinct colors for the edge. So this is zero knowledge since the verifier just sees two random colors in its view. And moreover, the verifier will catch a cheating prover on a false statement with at least inverse polynomial probability. So this is a non-trivial protocol, which you can then amplify by repeating many times in sequence to get negligible soundness error and preserve zero knowledge. So this is nice, but it requires repeating the protocol many times in sequence. And so you get a very long protocol. It would be very nice if you could instead just do many instances of the base protocol in parallel. You might hope to have this three-message protocol on the screen be your zero-knowledge protocol for NP instead. And you can show that this protocol is still sound. Parallel repetition very generally amplifies soundness, at least for statistically sound protocols. Now, that's good, but it was open whether or not this transformation preserved zero knowledge for this very basic protocol. So until this paper, this was the state of the art on this question. And in this work, we show that at least for a natural choice of commitment scheme in the common random string model, this protocol is not zero knowledge, assuming the hardness of learning with errors. And the way that we prove this is via a known reduction to Fiat-Shamir. So the Fiat-Shamir transform is a very general technique for converting public coin interactive protocols, so interactive protocols where the verifier just sends random coins, into one message protocols that at least heuristically have the same functionality as the original protocol. So the way you do this is the prover for the Fiat-Shamir one message version of the protocol will generate an entire transcript of the interactive protocol in one shot by sequentially producing the next prover message alpha I, and then hashing the entire transcript so far, everything up until alpha I, to get the ith verifier challenge beta I. This will allow the prover to generate an entire transcript. The verifier can check the hash values and check whether the transcripts would have been accepted. So at least syntactically, this gives you a protocol that's for the same language. The question is whether soundness is preserved. And heuristically, it seems to be the case that if the protocol on the left is sound, then the protocol on the right should be computationally sound against computationally bounded cheating provers. Moreover, there are a number of protocols in practice, on the internet that are fairly essential that rely on the soundness of this transformation, at least as applied to particular protocols of interest. So this is the Fiat-Shamir transform. And it's a big theoretical question that we are still trying to wrap our heads around, like how to reason about the soundness of this transformation formally. So it's been known for a long time that if you model the hash function as a random oracle, then the transformation is very generally sound. So if you're willing to believe, for example, that SHA-2 behaves exactly like a random oracle, then in some sense you're already done. but we know that this is incorrect. This is actually not the case. So there are some interactive protocols that are sound, and such that an ideal Fiat-Shamir transformation of the protocol would be sound, but for any concrete hash function family, you can show that the resulting protocol is unsound. These protocols are usually somewhat contrived, but it says that there's a lot more to be understood here about when the transformation is actually sound in the standard model. So our goal in this work and in a long sequence of works over the last few years has been to establish a stronger theoretical basis for this transformation, because the transformation has been around for a long time. It's very important, but it's only been in recent years that we've had any theoretical understanding of the soundness of Fiat-Shamir. So in this work, what we do is we give a standard model Fiat-Shamir instantiation for the parallel repetition of any commit and open protocol, like the example that I gave earlier. So in general, in a commit and open protocol, the prover sends a commitment to some string based on a witness that the verifier doesn't have. The verifier somehow selects a subset of bits that they want the prover to open. And then the prover opens this subset of bits, and the verifier checks some information about the subset that was opened. So this is what a commit and open protocol looks like more generally. And we give a Fiat-Shamir instantiation for all such protocols. And so what do we get out of this? Well, first of all, Fiat-Shamir is a round compression. So this gives a non-interactive zero-knowledge variant of any committed open protocol, as opposed to some prior works from a couple of years ago that only worked for some very specific protocols. Moreover, as I alluded to earlier, it's known that any such protocol with a valid Fiat-Shamir instantiation cannot be malicious verifier zero knowledge. And so this resolves the open question that I described earlier. So this is the first result is for 3-message protocols, and it's for 3-message committed open protocols. We have more general results than that. First of all, we have versions of this result for greater than 3-message protocols. And moreover, the committed open structure is nice for describing like a concrete result, but we have some more technical condition called having efficiently recognizable bad challenges, which actually governs when we have Fiat-Shamir instantiations. So those are our results at a high level. And the main takeaways that I want you to get from this are we have a much more widely applicable Fiat-Shamir instantiation than in prior works. Like I said, it was really just for a few protocols before that we had known Fiat-Shamir instantiations, and now I would say the class of protocols is much broader. Moreover, we resolved this intro crypto open question, so you can finally tell your undergrads, no, you cannot just repeat GMW in parallel. You have to repeat it sequentially to preserve zero knowledge. And finally, in the techniques, we get this really neat connection to coding theory, which I hope to get to in a few minutes. So now let me get into more details about how we prove the results. As in prior works, the Fiat-Shamir results go through this security property of hash functions called correlation intractability. So a hash family is correlation intractable for some sparse binary relation R if it's hard for an adversary to find an input-output pair of the hash function which satisfies the relation. So as long as there aren't too many points in the relation, a random oracle will have this property, but we're interested in whether particular concrete hash functions satisfy this hardness property. And in prior work, we constructed hash functions satisfying this property for relations that are actually functions. That is, relations where every input has only X, has only one output Y in the relation. And in the state of the art, we know how to do this based on the learning with errors assumption. This is due to Pikert and Sheehan. And the relations that they can handle are bounded polynomial time computable functions. So this is what we know how to construct, and we're actually going to use these, the Piker-Sheehan hash function directly in this work as a building block. So now let's see what correlation and tractability has to do with Fiat-Shamir. How does it translate? So let's just think about compiling a 3-message protocol like is on the screen right now. The Fiat-Shamir version of the protocol is on the right. And we'd like to prove that this protocol is sound. So given H, it should be hard to find alpha, hash of alpha, and gamma that corresponds to an accepting interactive transcript. So the way that you can prove that a correlation and tractable hash function suffices for this transformation is by the following arguments. Let's restrict the protocol to be very special. Let's suppose that for every first message alpha and every false statement, there's at most one verifier challenge such that the prover can come up with any accepting third message that would convince the verifier. So most protocols do not satisfy this property, but there are some interesting ones that do, and this is how prior works went about Fiat-Shamir instantiation. They restricted to this class of protocols. So if you make this restriction, then we can define a function which maps the first message alpha and possibly the instance x to this bad second message beta that would enable the prover to cheat. And then it's not hard to see that if the hash function is correlation and tractable for the function f that we just wrote down, then the resulting 2-message protocol on the right is sound. And the reason is that in order to find an accepting 3-message transcript, the second message beta would have to be the bad challenge f of alpha. So that's how it corresponds to correlation and tractability. So finally, if we can arrange for the function f to be efficiently computable, then we can build a hash function family H and a Fiat-Shamir instantiation based on the LWE assumption. So this is what I'm calling the bad challenge function paradigm that we saw in prior works. So, and this does give Fiat-Shamir instantiations, but it at a cost. It puts a large restriction on the interactive protocol. There can only be one bad challenge for every first message. So now let's analyze that. Let's try to do the same analysis, but when there are more bad challenges. So let's suppose that there are capital B bad challenges, beta, for every first, at most B bad challenges for every first message alpha. Well, then we can't define one function f that governs the soundness of this protocol, but we can define B of them. Just for I between 1 and B, define the ith bad challenge function to be the function that maps alpha to the ith bad beta. And then if the hash function family is correlation and tractable for a random choice of this f, or maybe just all of them, then you can still show that the protocol, the non-interactive protocol, is sound, but you have a security loss of 1 over B because you have to essentially just guess, or at least the naive reduction would just guess, which bad challenge the cheating prover is finding most of the time. So if B is only polynomial, then you have a polynomial security loss, and this is totally fine. We're happy. However, it's very common for in protocols for B to be gigantic, and so if B is exponential, then you don't get any meaningful results here. So the problem is whether we can handle interactive protocols that have a large number of bad challenges. And if you just think about most protocols of interest, if you take a parallel repetition of some base protocol, even if the base protocol has like 2 bad challenges, when you repeat it many times in parallel, you get exponentially many bad challenges. And the paradigm on the previous slide is not really enough to get an instantiation, at least a good one. Usually it's not enough to get any instantiation at all. So yeah, the question is whether we can handle protocols with many bad challenges. In the language of correlation and tractability, this corresponds to the question of whether we can instantiate CI for relations that are very far from being functions. So that's what we do in this work, not for general relations, but for relations that have nice structure like those that come from parallel repetition. So, very quickly, the relations that we consider are called product, we call them product relations. They're relations where we think of the output as being broken into T blocks. And we say that R is a product relation with this structure if for every X, the collection of outputs in the relation with X forms a product set with respect to this block structure. So it just says that, yi is in some fixed set. Each yi has to be in some fixed set Si. So like I just said, product relations, they could have exponentially many bad points in them. However, there's some nice combinatorial structure that separates them from general relations, which we don't really know how to handle in correlation intractability. So in the language of CI, our main result is that we can instantiate CI for product relations with some caveats. So you need to be in an information theoretic parameter regime where it makes sense, at least where a random oracle will satisfy the property. We end up needing, the parameter regime that we can handle, it does not exactly match the random oracle parameter regime, but it's fairly close. And we additionally need membership in these block sets S sub I to be efficiently decidable in order to get an instantiation. This replaces the old efficient computability requirement for functions. So this is our CI result. And let me explain just a little bit about how the construction works. The main idea is to have a hash function which first hashes down the inputs to a even shorter output than you need, and then expands that intermediate output via an encoding operation. So we take X, we hash it with some inner hash function, get some intermediate Y, and then we encode it with some error correcting code to get an output Z that we think of, again, as having T blocks to match the relation structure from the previous slide. And so remember, the security property we're looking for is that it should be hard to find inputs that hash to Z's where each of these Zi's lies in some pre-specified set S sub I. So again, this is how our hash function looks. And the idea here is that we're artificially reducing the number of effective bad points in the relation with this code. So before, so the number of bad Z's for every X according to the relation might be very large. There might be exponentially many of them. However, we're hoping, and we're going to instantiate things so that there are only a few code words, only a few Z's that are code words and lie in the relation with X. And that corresponds there being only few valid Y's in this picture, which will enable us to run the trivial 1 over B based reduction to the Y with when analyzing just the inner hash function. So we're going to have the inner hash function be the Pikert-Sheehan hash function based on LWE, and we're going to compose it with a nice error correcting code. So what property of the code do we want? That's the unspecified part of this picture so far. So it turns out that coding theory has exactly the right abstraction for this problem, sort of magically. The property is called list-recoverability. So this is like a generalization of list decoding. So in list recovery, the problem is as follows. You have a code. The code has T symbols, and you have some constraints on each of the T symbols. You want to find code words such that the first symbol of the code word lies in set S1, the second symbol lies in S2, etc., up to S sub T. And so a code is list recoverable if there are only polynomially many code words in each product set S1 cross, etc., through ST of the appropriate size, as long as the size of each SI is not too large. So that exactly corresponds to the reduction we were trying to do on the previous slide. And so the list recoverability, as I just described, is an information theoretic property we're going to be interested in an algorithmic version where we want to recover the total list of code words in these product sets in polynomial time, given descriptions of the sets S1 through ST. So this is the property we're interested in. It's come up quite a bit in coding theory, especially in the context of composition. But we haven't seen too much use of it in cryptography before. It's been used in maybe domain extension for hashing, but certainly not in the Fiat-Shamir context. So this is a cool new connection that came about from trying to solve this parallel repetition problem. So just in a little more detail, the list recoverable codes give a nice translation between coding theoretic notions and properties of parallel repetition of a parallel repetition protocol when we use it in the way that I described. So the block length of the code end up corresponding to the number of repetitions for your protocol. The alphabet size Q of the code corresponds to the challenge space for the base protocol that you're repeating. And then the input list size corresponds to the number of bad challenges. Those three are the most important parts of the translation table. So, we can now take our Fiat-Shamir question or our correlation and tractability question and translate it to a question about the existence of codes with the right parameters. If we can construct a code that turns our product relations into relations with only polynomially many bad points, then we can rely on the Pikert-Sheehan hash function. And again, this is a generalization of list decoding. So list decoding corresponds to the case where the sets SI have size 1, and you also allow for errors in worst case errors in some fraction of the symbols. We also consider an error version of list recoverability when we are trying to give our results for multi-round protocol. But back to Fiat-Shamir, let me just sketch again the proof of the construction of correlation and tractable hash functions for product relations based on LWE. We have this composition of the inner hash function due to Pikert and Sheehan with the encoding operation of a list recoverable code. And just from staring at the composition, you can drag out the parameters that you need from the list recoverable code to get good correlation and tractability. The ones that I wrote down are for the worst case situation where like all but one challenge is bad and you need to repeat Q times in that case in parallel to get a valid to get even soundness in the information theoretic setting. But whatever your soundness parameter is, you'll get out parameters for the code that you need to get a sound Fiat-Shamir instantiation, and then we construct codes satisfying these properties. So the key lemma is that you can get essentially any code that you would want for the situation by picking the right Poveresh-Vardy code and the right size random code that you can brute force decode and combine them with code concatenation. You can run the calculation and see that these efficient codes give you close to optimal parameters for what we care about. So finally, I just want to say quickly that we do extend this to multi-round protocols. We use the round-by-round soundness notion due to prior work, and we require that for each round of the round-by-round analysis, that the bad challenges are efficiently recognizable. In any such situation, we then show that you can repeat this protocol in parallel enough times and get a valid Fiat-Shamir instantiation. Again, by concatenating the Pikert-Sheehan hash function with the appropriate code. And so as an example, for a protocol that you might care about, we can get a Fiat-Shamir instantiation for a parallel repetition of a small field sum check or GKR delegation protocol. So a recent exciting work of Joale, Kurana, Kalai, and Zhang gave an instantiation for GKR over an exponentially large field where you don't need to repeat in parallel anyway. But our result says that you can extend their results to even small fields, some check and GKR. So that's all I wanted to say about our results. There are a lot of cool open problems that I think are still available in this area to work on. For example, we still don't know how to say anything about protocols that do not have efficiently verifiable bad challenges, or you can't finagle in some way to have efficiently verifiable bad challenges. A good concrete protocol to think about is the graph isomorphism protocol. In addition, the multi-round protocols, our Fiat-Shamir instantiations are still quite suboptimal in that they require making a sub-exponential hardness assumption on the underlying hash function, and so relatedly, they only achieve selective soundness as opposed to adaptive soundness, and then you need to do further leveraging to get adaptive soundness. So these are all things that one might hope to improve. And I think the biggest open question in the area is extending any of these results or giving any sort of interesting Fiat-Shamir instantiation for an interactive argument that is not statistically sound. The big prize here being the Killian delegation protocol for NP. So that's all I wanted to say. Thank you for listening to the talk.